Hi guys, welcome back. Today we will be talking about logical database design, and since this class is all about data modeling, we will be talking more about logical data model or relational data model. Very important class. That's our last step of database design before we actually start database implementation. So let's start. Let me minimize this and just a second. Then we will dive into logical database design. Right. So a little review. Second here. Just Right. Let's talk a little bit about what we did last class, and that would be advanced data model. We talked about subtypes and super types. Hopefully, you guys can give some examples now. So, example of super type would be a vehicle with subtypes car and truck. And if you guys remember, we talked about motorcycle, why it's not a subtype, because motorcycle doesn't have its own specific attributes. So we talked about attributes and relationship inheritance, and it means that both attributes and relationships are inherited by subtype from supertype. So if there's any relationship existing on the supertype level, they will be inherited by all the subtype. And same, applies to the attribute. We talked about specialization and generalization, top-down versus bottom-up approach on how to extract subtypes from supertype or combine subtypes into one supertype, which is generalization approach. Talked about completeness constraint, and within completeness constraint, we talked about total specialization rule versus partial specialization rule. Total specialization rule means that outside of the model, there is no other subtypes other than listed within the model exist. And partial specialization means that there are other subtypes exist, but we do not include those subtypes into our data model. Talked about disjoint constraint, and within that we defined disjoint rule and overlap rule. Disjoint rule means that the instance of the super type can be at a certain moment of time only can represent in a certain moment of time only one instance of the subtype, and overlap rule states that supertype can be one or more subtypes at the same time. We also talked about entity clusters and advantages of those to simplify, and most biggest advantage of clusters, entity clusters would be to simplify the model for presentations or for better understanding and to better see the overall picture. Right, with that, we're gonna move on to the logical database design. Today's long class, so we're gonna do it in two parts. During the first part of the class, we're gonna talk about theoretical theory behind logical database design and relational data model. And during the second part of the class, we'll do a couple of exercises, so you guys will have a chance to apply what we learned in the first part of the class in actual real life modeling examples. So we're gonna start from learning about components of relational data model. Further down, we already talked briefly about relational data model during our third class, modeling data in organizations. So today we will review relational data model in more details. We will talk about different properties of the relations, and later on we will talk about what is and what is not a relation. We will look at the differences between tables and relations. Also, we'll talk about constraints, what type of constraints exist and what do they mean for our data model. And further down, we will talk about referential integrity constraint, which is the most important constraint within relational data model. Thanks to this constraint, we're able to join tables together, so and subsequently retrieve data from multiple tables. All right, so let's start. And before we get into the details of the relational data model, I want to briefly stop at this diagram. We looked at this diagram already a couple of times when we talked about logical and physical independence, but here it's very important for us to understand where actually we are. We talked a little bit about business rules in the beginning, so we covered that in our third class. Then during the last three classes, we were working on conceptual data model. So we had to deal with entities, relationships, attributes. We talked about simple conceptual data model. We talked about advanced conceptual data models that included subtypes and supertypes. And today we will be talking about logical model or relational data model. So as you can see in this diagram, logical data model has a much lower level of abstraction. So it means it's a little more concrete. It has a little more details compared to conceptual data model. You guys remember abstraction is highest at external data model, where we don't really need to know a lot about database implementation details. We just need to know basics as users. Then we work on conceptual data models that has a little lower level of abstraction compared to external data model. It has more details related to the database. We already have entities, attributes, and today we are going to add more details to conceptual data model. So logical data model has more information. It's ready to implement database. So when we will be done with logical data model, we are almost ready to start working on our database. So we are currently here at logical data model. So we are going to talk today about relations, constraints, and we are not going to spend time on normalization, but normalization module is available for you guys. So if you are going to look at that, you can attempt extra credit on the homework. All right, so we are moving from conceptual data model, and we are going to work today on logical model or relational data model. So a relational data model was introduced by Edgar Codd. Edgar Codd developed main relational database model rules. Those are 12 rules that are listed in your book. You can review them. So this model was introduced in 1970, and it was a big step compared to all the previous models that exist before that. So Relational data model is pretty much a base for all new modern databases. Majority of the companies now use relational databases, which are created based on relational data model. A relational data model is a representation of a relationship within the database. So in order to create relational data model, we need to take our conceptual data model and add more implementation details to that. So when conceptual data model has a very vague idea of identifiers, of keys, relational data model is all about how to create relations, how to create relationship between relations, and how to connect those relations together using foreign key, primary key constraints. And in the base of the relational data model lies relation. So let's talk about relation. Well, before we can talk about relations, let's talk about components of relational data model. Um, well, first of all, it's relations or tables. Well, as we know, table is a two-dimensional data structure that has rows and columns. Not all tables are relations, and we're gonna discuss in more details what is a relation and how they're different from tables. So in addition to relations, we have attributes or columns. Those are specific characteristics of entities, and we did look at those a little bit during our uh, model and data in organization class, but today we're going to talk about that in more details. So attributes are columns. So we also have rows that in the concept of relational data model called tuples. Those are individual records or rows within a relation. Those if you guys remember, when we talked about entities, we talked about entity instances. So here in relational data model, those tuples or rows are representations of certain entity instances. There's also keys, and keys are we have primary keys and foreign keys. Primary keys are unique identifiers of specific tables, and foreign keys is the same key but placed into another table in order to be able to connect this specific table to a new table. So primary key, foreign key relations allow us to connect multiple tables together within a relational data model. And of course, we have constraints and relationships. So constraints, we have domain constraints, integrity constraints. We're going to talk about those. And relationships is a connection between two relations that allows us to connect those relations together in order to retrieve data. Right. So what is a relation? A relation is a named two-dimensional table of data. So it consists of rows and columns. Key point here is it's named, so it must have a name, and it's two-dimensional. So there are columns and rows. And as we remember from the previous slide, columns represent attributes and rows represent specific instances of this relation or instances of entities in conceptual data model. So we have an example here of a book relation. So this book relation I currently have 6 attributes: book ID, title, author, published date, genre, and ISBN. What is the primary key of this table? It's book ID, right? So book ID is unique, and book ID represents a primary key. What can be a what can be a candidate key for this relay for a candidate key for this relation. It can be ISBN, right? Because it's also unique. However, as you can see, it's a long one, so we replace that with book ID. And book ID in terms of relational data model is called surrogate key. So that's a key that was created by humans or by a database engine to uniquely identify each book, because ISBN is a unique identifier. However, it's, as you can see here, it's very long. So we cannot use this ISBN as a unique identifier overall. We can, but it's going to be difficult to maintain relationship with tables. And also later on, when we'll be talking about performance, we will talk why we create surrogate keys, and those are mostly for performance reasons to improve the speed of combining different tables together. Right. So what is the difference between relations and table? And what defines a relation? So here's a piece of information for you. All relations are tables, so but not all the tables are relations. So let's look at the example here. In example one, we have a relation student. So relation student has four different attributes. Those are columns, right? And we can see three different rows for this relation, and those are instances. We also see a table employee. Table employee also has attributes, five, actually six attributes here, and certain instances for employee one, two, and three. Let's look at the differences between the data in those two, given that we know that student example one is a relation student and example two is a table. So what is actually the difference here? Well, if you can see, I highlighted address field. So the address attribute has a lot of information here. What kind of attribute is address? It's composite attribute, right? So it has information about address, city, state, and zip code, right? So how about phone numbers? Phone numbers for example, employee three has multiple phone numbers. So what kind of attribute is that? It's a multi-valued attribute, right? So um, let's see what defines the relations. So here we have requirements for a table to qualify as a relation. So first of all, it must have a unique name in the database. Remember, so when we talked about relations, we talked that it's a named table with attributes and instances. So every attribute must be atomic. So relations do not allow multi-valued attributes, and they do not allow composite attributes. Every row must be unique, so we can't have two exactly the same um, rows within the same relation. Um, Attributes must have unique names. So in terms of relations, we can't have two exactly the same, two columns that are named exactly the same within a certain relation. We also did talk about that a little bit in the past, but for the relations, the order of columns and the order of rows is irrelevant. So it doesn't really matter how we store data in this relation. So for example, in this product relations down here, you can see total of five different products represented. 101, 102, 3, 4, and 5. And they have a certain product ID, product name, and categories. What's important to understand that if we replace the order of columns, so for example, we first list product name and then second product ID and then price and then category and then stock count, it doesn't really matter for the relations. So we can put those columns in any random order we can, and that is not going to affect data in these relations. The same applies to the order of rows. So it doesn't really matter if we store product t-shirt on the first line or book on the first line. So as long as the entire row is together, it doesn't really matter at what order those rows are stored within a table. That's very important. That will come very important when we will be populating data in our tables for a team project. And also, last but not least, data in relations can have null values. As long as primary key is not null, and as long as our constraint allows to have null values, data in the relations can have null values for certain attributes. All right, so those are requirements for a table to qualify as a relation. Those are very important to understand because we will get back to those requirements a lot during today's lecture. Right. So let's look at an example, another example. So we have employee one relation, employee one table on the top. And as you can see, we have multi-valued attributes and course title. So for example, employee with employee Margaret Simpson, she took 2 courses as PSS and surveys. And another example of that is Chris. Chris also took 2 courses. So that means that this table represented on the top is not a relation because relation do not allow multi-valued attributes, right? The example on the bottom, employee to, is a relation. Here you can see that we added more data and we created a specific record for Margaret for another course. So at this point, we don't have any more multi-valued attributes. We replaced this multi-valued attributes with additional row in that we inserted in the table. And that is why the table on the bottom, employee two, is a relation, and table on the top that has a multi-valued attribute for the course title is not a relation. All right, so let's look at the example, and we're gonna do it the same way as we did in the past. We're gonna have a couple of examples where I want you guys to identify whether a certain table is a relation or it's not a relation. So let's look at this example first. We have a customer data here, and I want you to identify whether this is a relation or not. And here on the left side, I have a little cheat sheet for you that explains or specifies what needs to happen for a table to qualify as a relation. And as we talked before, all attributes must be atomic, so we are not allowing multi-valued and composite attributes. All rows must be unique, and all attributes or columns must have unique names. So please pause the video, think, and I will explain the answer later. All right. Hopefully you have your answer by now. So it is a relation because every attribute is unique. We don't have any repeating rows here, and all the columns or attributes are also unique. So this table customer is a relation, so it satisfies all the requirement of the relation. Uh, let's look at another example. Same idea here, so I'm gonna please think, analyze, and pause the video and let me know whether this table is a relation or not. Okay, so this table is not a relation because of the multiple reasons. So first of all, we have we have multi-valued attributes and we have a composite attributes here. So for example, address is a composite attribute, so it has address and city. Skills is a multi-valued attribute. So well, those are both not allowed in relations. Um, every row is unique. However, we have two columns or attributes. They have exactly the same name, department. So that is why this is not a relation. Okay, so we talked about relations. We know what is a relation. Now let's talk about attributes. Attributes are a very important component of relational data models. So attributes similar to conceptual data model attributes that we identified for entities a couple of classes ago. Those are specific characteristics of a relation. So each attribute has holds a specific value or a specific piece of information. Attributes in the concept of the table or the relational data model are columns in a specific relation. So they store certain pieces of data. And here we have an example of customer relation attribute. So this is a customer relation, and it has a total of 6 attributes. Those include customer ID, name, first name, last name, email, phone number, and address. Those are all attributes of customer relation. So here's an example. I want you to look at this example and identify books relation attribute. And it's pretty simple. So um, we have columns, and those would be attributes of the book relation. So ISBN, title, author, genre, year published, and publisher will be attributes of book relations. So columns are attributes. Right. So talked about relation, talked about attributes, now tuple. Tuple is a row in a relation, so it's one certain row. In this case, for example, row with customer ID 1 is going to be a tuple of employee relation, also super simple concept. Right. So keys. Keys are attributes or a combination of attributes, can be multiple attributes that identify specific records within relations or help us connect relations together. Within the relational data model, we have two different types of keys. We have primary keys that uniquely identify specific tuple or row in a relation. So those helps us to find rows based on a specific field. So there can be two exactly the same two rows that have exactly the same primary key. So primary key is a unique for the entire relation or table. So for example, if you have an employee relation, the primary key there will be employee ID. And employee ID must be unique for each row of the table. So it can't be two exactly the same employee IDs within this relation. So for SDSU, for you guys, if we have a certain data related to students and we store it in the student table, unique identifier of the student table is going to be your red ID. So there's hopefully not two students who have the same red ID, and your red ID uniquely identifies you as a student. Okay, so that is primary key. Um, Foreign keys are attributes that help us to link two tables together. So foreign keys are primary keys of one tables that are placed in another table. So that helps us to connect two tables together. Um, so for example, when we talk about student and department, we can add a department table has a department ID. So if we add department ID to a student table, we would know what department each student belongs to. And we will be able to retrieve data from both student and department table together based on this constraint or foreign key for the department ID that is placed into a student table. Keys, both primary and foreign key, can be simple, which is one field, or composite that includes more than one field. Good rule of thumb is to use more simple keys than composite. They simple keys are much better for performance when we need to connect two tables together. And we're gonna get this last bullet point here. Keys are usually used as indexes to improve data retrieval. We're gonna talk more about indexes in our class 8 when we'll be talking about performance and tuning. So we'll get back to this concept of creating indexes based off key fields. Right, so primary keys, example, in customer table, we have a primary key customer ID, it's unique, so there is no two customers which have the same customer ID. Now, is customer ID simple or composite? It's simple, right? Because it's only one attribute here, customer ID. Right. Also, let's look at this relation a little more, and let's look and decide what can potentially be a candidate key here. So candidate key can be email address, but only for this specific relation because it's unique. Well, in general, can email be a primary candidate key? Yes, if it's unique, but some people have multiple emails, so when it's not unique or when it's a multi-valued attributes, it can't be used as a candidate identifier. All right. So primary key and foreign keys. I want us to look at this example. That's an example from the past. We looked at that before. So in this case, we have two different relations, table or tables. We have product table and vendors table. And again, as we remember that all the relations are tables, but not all the tables are relations. And in order for table to be a relation, it needs to have certain criteria, and we talked about those criteria. But in the future, we'll be using those words. We will be using those words together. So for tables, in this case, we're going to talk about two tables, product and vendors, but those can be relations too. So table product and table vendors, they have a relationship, and it's binary relationship in a relational data model. Vendors relation has primary key of vendor code, and product relation has primary key of product code, but we have a foreign key of vendor code, which allows us to connect vendor table and product table together. So this is a concept of foreign key and primary key relationship between two tables. Let's look at the example. So let's identify what is the primary key and foreign key relations below. So we have a student relation, enrollments, and course. I'm going to let you, we did a similar exercise a while ago, but I just want to get back to that. In terms of relational data model or logical design. So I'm gonna let you guys look for that, look at this data for a minute and see what kind of keys you can identify here. And if you remember, we talked about finding similarly named attributes or columns that have similar data, and those are most likely are going to be primary keys and foreign keys. So I'm going to pause the video for a second and I will give you an answer. All right. Hopefully you got it right. So here we have a student relations with the primary key student ID. We have a course relation with the primary key of course ID, and we have an enrollment relation that has a primary key of enrollment ID and foreign keys of student ID and course ID. That allows us to connect those three relations together. All right, so constraints. Constraints are rules that applied to data to maintain integrity and support business rules. So what does that mean? So every table has a certain set of rules that is applied to the data stored in this table. So constraints ensures that data stored within a table is consistent. So and those rules are applied to the data. Within constraints, we have two different types of constraints. We have domain constraints that are constraints for a specific table, and we also have integrity constraints. Integrity constraints are constraints that make sure that the data stored within tables or set of table supports integrity rules. Right, so a little slide here for data types reference for you guys. We will be using different data types a lot when we will be working on database design. So those are very basic data types. There is much more than that, but for the scope of this course, that should be enough for us to create simple databases. So we have integers, or those are whole numbers, can be negative, can be positive, can be zero. We have decimals. So decimals are numbers that have decimal points, okay? We have character strings that are just words and or a combination of set of characters when it in terms of the database. Those are called chars, and varchars. So when we talk about char or a character, it's a one letter. When we talk about varchars, can be multiple letters, can be a combination of many letters. Boolean, true or false, very simple. So very good use of the Boolean values is in your homework. If you remember question 5, we had is removed attribute added to the posting when posting is removed. So that would be an example of Boolean. We also have date time. So, and those are just to record a certain date or time of an event. We have, it can be date time, can be time steps. So different types of data types that allows us to record date and time. Right. So now for the main constraints, we're going to use a specific data types that describe data stored in a specific table. The main constraint is table metadata. If you remember when we talked about metadata, metadata is data about data. So the main constraint is a set of all possible values that specific attributes can have. So the main constraint defines rules that apply for a certain field, and they make sure that only this specific data type is stored within a certain column, a certain table. So, for example, we have the main constraint for employee relations here. So for example, for employee ID can be integer, so number without decimal point. First and last name are characters that cannot be more than 100 characters long. It's probably like too much because we usually don't have names more than 10, 20 characters, but just in case, I mean, we store it as a 100 characters variable character. Salary, well, decimal, and hire date is a date. So with this domain constraint, which is a metadata for an employee table, we ensure that every time we insert certain rows we put certain rows into a table, the data in the certain rows that we're about to insert have specific values for each attribute. So, for example, if we're trying to insert some set of characters in the salary field, the main constraint for employee table data will not allow us to do it because data type is not going to match. So salary is only going to accept a decimal. So if we're trying to insert some characters or numbers in the hire date field, our database constraint will not allow us to do it either because data type for hire date is date. So that hire date must be date in order to be inserted in the database. Excuse me. So the main constraints ensures that the data that we are putting in the table satisfies certain criteria, and all those rules are applied to this data. So those are the main constraints. Here's an example of the main constraint for a certain group of tables. So we have invoice attributes, we have customer ID. That's actually the main constraint for the invoice table. We have a customer ID, customer name, and so forth. And in the domain constraint, we specify the type and the size of a certain field. So in this case, customer ID, for example, is a character. So it's not necessarily a number. But and there is a size to that. So customer ID should not be longer than 5-character long. Customer name should not be longer than 25-character long, and so forth. So this is an example of the main constraint. Okay, so the main constraint specifies the size and specifies the data type. Okay. All right, so let's look at the example. I want you to look at this course relation or course table and suggest the main constraints for each specific attributes or column. And I put a little data type reference for you guys here, integer, decimals, string, boolean, or date, so you'll have something to work with. Right. So let's look at what I have here. So for course ID, I have an integer, but it's probably can be a character here. It just can't be we don't have a size at this point, but based on this data, integer is probably a better option. We have course name, which is variable character 50, probably can be 20, but I mean 50 is good. Remember, when we talk about defining domain constraints, the size of the field matters, but we need to allow a little extra to make sure that when we insert larger value, our table still supports that. And plus, when we're talking about defining the size of the data, we will talk more about that when we'll talk about physical database design and segments. But when we define the size of the field, we actually talk about allocating the size of the physical storage for the table. And when we're talking about physical storage is cheap. So pretty much hard drive space doesn't cost us much. So when we define the domain constraints for a certain relation, sometimes it makes more sense to go a little higher than expectation. So in this case, when we talk about course name, yes, course name is kind of short field, but I mean, can we allocate a little longer space for that just in case? Yes, of course. And it's probably good to allocate a little more space that we think we might need. Okay, so that's why I put variable character 50 for course name. And for the instructor, I have also varchar 50. And for credits, it's an integer. So here's my domain constraint for course relations. Another example for you guys to work on. So pause your video and suggest domain constraints for the product relation. All right, so here are my domain constraints for product. Hopefully you get something similar to that. I have integer for product ID, varchar 50 for product name, decimal for price, integer for stock, and expiration date as a date. We talked about we talked about domain constraints, and now we're going to talk about integrity constraints. So there's two types of integrity constraints: relational integrity and referential integrity. Relational integrity constraint states that no primary key attribute can be null. So meaning that if we set a specific primary key, all the data we insert in a certain table must have value for this primary key. Okay, so all the primary key must have values, and the primary key cannot be null. So that is a concept of relational integrity. So primary key in a relation must not have null values. And we have an example here in, for example, author relation. Primary key is author ID, so we have no null values in author ID. Right. Referential integrity constraint. Referential integrity are rules that helps us to maintain consistencies between the rows of two related tables. So, which is implemented through foreign key, primary key relations. Referential integrity states that any foreign key value in a relation of many side, remember when we're talking about relations of many side, foreign keys always sits on the many side of relation. So foreign key in the relation of many side must match a primary key value on the relation of one side. So this is much easier to understand when we look at entity relationship model. So remember how we have one-to-many relationship, for example, between student and course. So one student can take many courses. So many is on the course side, one is on the student side. So one student can take many courses, right? So in this case, foreign key is going to sit on the student side. So foreign key course ID is going to sit on the student side, and we are going to have many courses on this many side of relationship. So within referential integrity constraint, we have multiple, important part. So a foreign key on many side of relationship must match all the primary keys, or foreign key can be null. So if there is no match within a primary key table, it can also be set to null. It all depends on a specific rule applied for a certain table, whether we allow foreign keys null or not. But if we do, foreign key can be null too. And within the referential integrity constraints, we have various rules here. So we have delete rules, insert, update, and all of those rules must be set when we create tables within the database. And here's a couple of examples. For the delete rules, so we can have restrict, cascade, or set to null. So restrict rule states, if we delete restrict rule states that we cannot delete from the primary key table or parent side of the relationship or one side of the relationship when we have a record in many side of relationships. So that means that if we have dependence on the many side of relationship, we cannot delete rows from the primary key side of the relationship. Cascade states that if we delete the row with a table that has a primary key, we automatically delete all the rows that have foreign keys. And set to null, if we delete rows from the primary key table, we set all the values for the foreign key table to null. And if you can look here, remember the referential integrity constraint allows us to have foreign key null value. Okay. All right, so that's referential integrity constraints. Very important. Let's look at the example. So here we have customer table and order table, and customer table is on one side of relationship, right? And order table is on many side of relationship. So one customer can place many orders, right? So customer is one side, order is many side. So for those two relations, we have primary key in customer is customer ID, in order is order ID. So customer ID in order table is a foreign key that allows us to link orders to customers. So for example, first order 101 belongs to customer 1, order 102 belongs to customer 2, order 103 belongs to customer 3. So with referential integrity constraints via foreign key, we cannot insert rows in the order table if the customer doesn't exist. So for example, if you're trying to insert the row in the order table with customer ID 55, if you look at customer relation, 55 customer ID doesn't exist. So if we insert something in the order table for the customers that doesn't exist, this data will not be allowed to insert based on referential integrity constraint implemented on the database side. For the deletion, you cannot delete customer one from the customer table because this customer has data in order table. For the update, so you can't update customer ID on the customer table if the order table doesn't have if the specific customer does have corresponding orders. And again, that all depends on the constraints. So if our constraints allows us to do it, then we can do it. But in this case, here is an example of the restrict constraint on insertion, deletion, and update. Okay. All right. Here's an example on how referential integrity constraint is implemented within tables. You guys will be doing that during your team projects. So, for example, we have two table definitions here, customer and the order has a constraint order, oops, order foreign key on customer ID that references customer ID in customer table. So that is something for you guys to look at when you'll be working on a team project. Don't need to worry about that now, so just save it as an example. All right, so how do we connect, how do we correspond a relational data model to a conceptual data model or entity relationship model? So entities or entity types correspond to relations or tables. Entity instances correspond to rows in relational data models. Attributes are columns. One-to-many relationship correspond to referential integrity constraint or foreign key, primary key relationship in relational data model. Well, those are simple concepts, but translation goes a little bit more complicated. So we have set of rules on how to convert conceptual data model into logical design. So for example, composite attribute, multi-valued attributes, many-to-many relationships, ternary relationships, all of those will require a little bit of work when we were converting conceptual data model into the logical design. Oh, and also, it's very important to understand that word relation in the relational database is not the same as word relationship is entity relationship diagram. Word relation represents a table or a relation. A relationship represents connection between two entities together in in entity relationship model. All right, so uh, we talked about the concepts of entity or of relational data model or logical design. And now we are going to talk on how to convert conceptual data model into relations or tables. So, how do we get from this diagram on the left that represent entity relationship diagram into tables on the right, which is something that we have in the database? So, how do we get from one model to the actual database? In order to get there, we are going to we need to get from conceptual data model to internal data model. In order to do that, we are going to create a logical database design. So today we will learn on how to convert existing entity relationship model into logical design in order to create the actual tables in the database. Right. So here's an example of the logical design for Pine Valley Company. We looked at Pine Valley Company a couple of times already during the previous classes. So that is a logical design schema for Pine Valley Company. And as we can see here, we have a set of four different relations. We have customer ID circled here as a primary key in customer table and underlined in order table as a foreign key. So this is a logical design that we will be creating today. And we will be creating this logical design based on the set of rules that we will discuss after the break. So let's take a break, and after the break, we're gonna talk about how to create logical designs, and we will at the end we will have a very good foundation for creating data tables. Right, so let's stop right here. Let's take a break and let's get back to the actual practical exercises.